Okay, so hello everyone. Um, Welcome again to the class. So, suppose that this is the third class, and we have at least discussed until the inverse function. Is there any questions before we continue? Any questions beforehand? Okay, so I hope you get familiar to inverse. If you want to get into details, you can learn more if you take my basic of math later. And if we have time, we can have more exercises. But let's continue, and still on the inverse, I would like to just to get into the what we call the logarithmic functions. Okay? So I will just take some quick review on what we are going to have. So in the previous page, we learned that the inverse, let me just write again here, that if we have this f inverse of x, which is equal to y, then we could exchange this and making the f of y equal x, okay? And then we also have so if we have exponent or exponential function, and let's say this is f of x equal b with power of x, with b is a constant we call the base, okay, if you remember. Then the inverse is called logarithmic function with base b, and sometimes we are taking by log and then we write b like that, and then this is the coefficient, okay? Or maybe you could just write down that if this is our inverse, then we can write log base b, okay, and then x, this is equal y. And this is pretty much are going to be inverse with the exponent, which is b with power of y equal to x, okay? So if you think logarithmic functions, it is actually an inverse of the exponent, which means graphically you can make the graph, the exponent, and then you can mirror. You can mirror through the y equal x, and you will get the logarithmic functions, okay? And of course, this is true if, so this is true if b is positive and b is not equal to 1, okay? Okay, just let me take this a little bit, go to the right here, and let me just draw a very simple curve to illustrate the exponent and the log. So let's say this is the y equal x, okay, let's say that is the y equal b with power of x, and then we have probably that will be the y equal log b of x b should be greater than 1. On the right side, you will see some different base. 5, 10, 3, 2, etc. And in scale, or perhaps you learn in physics or maybe chemistry when you learn about pH, you are using this logarithmic scale because it fits perfectly, right? Because you have like maybe millions units that you can simplify, and then you can see the differences through that millions by taking the logarithmic scale. Right? You remember maybe experimenting with the acid and then try to measure the pH or the base, right? Okay. And then if you take some time to think about why every scale of 10, we can take this as 1. Right? Do you know why? Why is log 10 is 1?
So it's 10 with the constant.
Yes, but with 1, why they define like that?
What is the visual?
Why this log of base of 10, we take it as 1?
Simpler, easier.
Yeah, it's easier because one argument is because we are living in a base of 10. Like our hands, it's easier to count with hand. Well, this will be a long story, but I'm going to make it short, okay? Because it's easier to count and measure, okay, for the sake of the research. And then we have several property that perhaps this is going to be useful for you. Okay. The logarithmic property, the multiplication inside the log, okay, inside the log, with the same, of course, the same base. You can separate this log, and if you have this division, you can also separate by taking minus. And then if you have the exponent inside, you could get the exponent and write in the front of the log. Okay? And I think this is very basic, right? But somehow, in our calculus, you will see later that this will be really useful, especially when you simplify some algebra, some algebra expression. When you find when you need to find like a solution, this is quite helpful, okay? Especially if we have a logarithmic function. Okay. Okay, but this is just a quick review. Okay. Let me check. Do I have the okay? Okay, another element that is essential in element that is essential in our course is the natural log. Okay. So we have at least tried to get into the number e, which we call the natural number or the Euler number. Then we also can define this e with log, which certainly give you, if we take log with the base of this constant or the number e of x, let's say this is our function, we can simply write ln x, right? And this is pretty common. You already know most of it, right? And again, the natural number is actually coming out from both nature. You have the populations, you have any other statistics, and you have when you take photos, some say that when you have a good ratio, what we call the golden ratio, your photos will be really, really good, artistically good. and then some saying that the number is the same as the e. Also, it came in nature when you see some plants, some shells, and you can take some and you make some rectangle. I don't have the picture now, but maybe later I will show you. And you have taken some part of it. It will have the same ratio. It will have the same ratio. So plants, some seashells, perhaps in astronomy, perhaps. I guess it will be the same ratio. So again, because this ln is the same thing as the log, just the different writings. So everything should be applicable. So when we have ln x equal y, then we could apply that. We can have the exponent e with power of y. This is equal to x. Okay. So if you take ln and then plug in inside the ln, the e to the x, then this is going to be x for all real numbers. Okay. And if you take the ln x as a power, it's also getting x, which this is going to be positive. And then of course, because of its property, the ln e is equals 1, right? We can also write, for example, if you have the, let's say x with power of r, a constant, can be a number, and then we take the e, ln, and we put inside the x with power of r. It means that we can take r ln x like that when x is positive. And another law that perhaps important. So this is the graph, the inverse, okay, between e and ln. Another law that is important is, we call it change of base. Okay, so log, let's say we have base of b, then we can actually input with any base. So if we want to, for example, this can be log x log b, but it doesn't have any base, so we can just plug in any base, anything. Okay, but for simplifying, maybe just e, right? So we can take this into ln x ln b. We can take the theory from, let's say we have this, okay, and then we have this, right, from the forms. And then if we take both sides, we take, let's say, take ln, right? And then you get y. So y is moving from here, go here. So we are going to have ln x over ln b. But it can be in any base. Like if you want to make log with base 3, log with base 3 is still okay. But anyhow, you could just change this with any base. Pretty useful. And of course, if you remember the transformations, how to make a new function from all functions, then you can also combine this logarithmic. Okay. If you want to make ln x plus 1 or ln x minus 2, and you can just move the graph. Okay. Okay, that's a quick review. Okay. If you want to get into details, then I will give you more in the basic of math class. But I think most of you already learned this, right? Okay. So you can take this like refresh your memory and maybe warming up. After this, one more about inverse. That is the inverse of trigonometric, and then we can move to the calculus part. So up until now, this is like a functions, not really calculus. Okay, now let's move to the what we call the inverse of trigonometry. Okay, we start with this graph, what we call the y equals sine. Okay, and if we take this horizontal line, okay, this red line here, it is concluded that this trigonometry is not it cannot be, or we don't have any inverse from this, right? Because of the horizontal. It's not one-to-one function. Okay. But we do have that sine inverse, right? The arc sine. How to get the arc sine? We need to restrict the interval. So if we, for example, if we take, let's say from here up until here, so let's say this is minus pi over 2. If we take between this interval, we can have the inverse, right? Okay, so this is going to be, so y equals sine x, and we need to define the domain, right? So domain will be from, let's say, minus pi over 2 until pi over 2. And then remember that, let me write the inverse. So if this is y equal, if that's f inverse of x equal to y, then f of y equal to x. Then if we have sine inverse of x equal to y, then we can also have that sine y is equal to x. And of course, because inverse is changing the domain and range, then we are going to have this is also true. Okay. So if we make the x between -1 and 1, then sine inverse x is number between negative pi over 2 and pi over 2. Okay. And all the rest should be the same, and we are just going to implement all the inverse law and the trigonometric. So if we have sine inverse sine x, this is going to be this equal x. And if we have sine and then sine inverse x, this is also x. This is true for this domain. Okay. So the sine inverse x, so f of x equals sine inverse x, has domain, we include the -1 to 1, and range okay. And the same thing with cosine and also tangent. Okay. Okay, let me continue for a while. I think we can move to the limits. Okay. We're going to see the inverse function again in the calculus part. Okay, don't worry about that. So limits and derivatives. Okay. So as I mentioned, I think in the early classes, that the first thing we are going to see are the tangent. Okay. So tangent, as the name suggests, is actually how the curve or the line or any graphs will be touched with one point. Okay, so imagine you have like a circle here, and you have a line that is touching precisely on one point. Precisely on one. So you need to imagine that this is going to be one point. So we call this is a tangent. Okay. So if we take, for example, another example here. If we take point P, okay, if we take point P and then we draw a straight line, we say that this straight line has a tangent. Okay, has a tangent. Okay, has a tangent line. Okay. But if you look, we have this line is of course crossing this. We need to specify at which point, that the tangent will be located. That will be, because every time you move this B, you have different tangent. Okay? You have different tangent, right? And the tangent will describe the steep or the slope, right? If it's like this, okay? And you can have like positive, negative, or even zero slope, right? Okay. So you can also say this is slope or how steep the graph is. Okay. Now let's observe. Let me make this. Make it here. Make it here. So let's say we have our curve y equal x squared. Okay? It's a normal x squared. And let's say we have p, okay, 1, 1 at this point here. Okay, we can imagine that we have the red line here, which is, we call it tangent. Okay. And then at the same curve, we try to observe another point. We say the point Q, and we just put x squared. Okay, so you can put with any numbers. So let's imagine and let's play with this Q. So this Q and P, if we take line between these two, we call this is a secant line, meaning that this line is cutting the curve. Okay? That is the secant, meaning, okay, cut the curve. So let's name this a secant line, and this is the tangent. So if we want to find the tangent line, okay, tangent line equation, okay, before we learn limit, derivative, and so on and so forth, let's just try to approximate. Okay? Let's try to approximate. Okay, so this is before we implement calculus. So approximate this this red line through this blue line. Okay? How? We are going to put some numbers. So the numbers, or if you remember, we have the gradient, which is the delta y over delta x, right? And in our case here, the gradient of the point PQ, so let's start from PQ. We can start with the y is x squared minus 1, right? This one here. So this is delta y, delta x, right? Okay. And then delta x will be, we are taking x minus 1. So 1 is probably here. This is, let's say this is x, okay? Okay, and then let's say we have x and then we have several m. So take x from, maybe we could take to the right side. Let's say 1.5, okay? Of course, if we take x equal 1, it will be undefined. So let's take a number that is nearby the point P. You can take first 1.5. You can try using calculators. But I will just give you the result here. It's 2.5, and then taking maybe 1.1, okay. And it's going to be 2.1, and then taking 1.01 will be 2.01, and you can take more 0, and then you will get. You'll see the patterns that it's going to be getting close to 2, okay? Well, if you know calculus and you learn how to find this, I bet the answer is 2, right? Okay. But if we just look this and try to find with some decimals, maybe you could also try, this is from the right side here, you can also try from the left side. So we could try 0.9, 0.99, 999, right? Okay, and I believe the answer will be 1.999, something, right? So we see that they are actually, we are getting something. We are getting something, and it is close to, I think, close to number 2, right? Okay. And then, okay, and then so let me write here. So the approximation suggests that slope should be m equal 2, okay? And now, how to deal with this? We invent or we create a tool called limit. So then, limit concept was born, and we'd say that limit as q getting close to p of this m pq is the m of the tangent line. So we can write limit as x approaching 1 is 2. But how to solve limit in computation, that will be another story. But at least from this whole table value, you can see that, okay, it seems that it's equal to. So the limit is actually something that we engineer, and we create to approximate something. Okay. So is it exactly the same? I mean, if we compute this, is it exactly 2? If we ignore limit, is it exactly 2? No, actually no. It's close to 2. But with limit, we kind of made a new definition that this is 2. Right? Okay. Yeah. So the limit is a concept that is, if we could imagine, if we move to the wall, we are never touch the wall, but we are getting close to. Even like 0.999, it's almost 1, but it's not exactly 1. Okay, so that's the limit. Okay. Okay, that's just introduction. And then another thing, okay, aside from the tangent problem, Okay, what I want to show you, let me, okay, so let me move to here. Okay, this is just to show you, how we could approach the tangent line. So we could approach like from really from the right side and then getting close. You see that the secant line is getting closer to the tangent line. It's getting similar shape, right? And then if we see from the left, okay, and then it's going here, and then it's also getting closer. So you can imagine that when Q is getting really, really close to P, it's pretty similar, right? It's pretty similar. And again, it is a concept that is close by, not exactly the same, but with limit, we can say, okay, that's the same. Okay. All right. Now, another. Another things in limit is what we call the velocity problems. Okay. So let me just write some example here. So suppose a ball drop from observation deck of a tower, let's say any tower, 450 meter above the ground. And then it says that we need to find a velocity of the ball after 5 seconds. Okay, before we get this, let me just give you the idea. So let's say this is the ground. So ground, and then we have a ball here, and then we have the 450. Oh, I forgot to mention. From the Galileo observation, we have these equations. Okay. So we have this. So this is the distance. Okay, the distance. Okay. Maybe write this is later on. So what should we do to find the velocity? Okay. So first is, what is velocity? What is velocity?
The initial speed plus acceleration.
Okay.
Per minute. You understand?
Yeah, I know your idea. But let me just write the average velocity that is, by definition, I believe you learn. So the average velocity is change in position, right? and then the time elapses, right? So how to know the position? How to know?
Make diagram.
So this is actually kind of not complete information that we get, right? So we need to assume, perhaps assuming something. So we need to find the velocity after 5 seconds. So suppose that, okay, the ball is dropped, and then 5 seconds later, so it means that it already has something, right? So we need to assume maybe we need to have either, so we know that it's 5 seconds, that is the initial condition. And how about the next condition? So let's say we are going to have like 5.1 or 5.2, 5.3. Okay? So let's say that is the change position. So let's just compute using that point. So let's just focus on, let's say 5 and then 5.1. So 0.1 seconds, okay, the difference. So let's try to compute that. So if we take the s at 5 and then minus s at 5.1, okay, and then divide by 0.1, it means that we are going to, this is 4.9 and then 5, oh sorry, I made a mistake. Should be that. And then squared minus, okay, mathematically you can compute this, maybe factor out 4.9, 5.1 squared, 5 is 25, 0.01, 2501, right? 2501, 2501, 4.949 multiplied by 10, so 4949, right? And what's this? Meter. Okay, so meter per second. Okay, it seems that we get something here, and let's do similarly with different times. So we say we take 5 to 5.1. Let's make it shorter. Maybe 5 to 5.05. And then make it shorter, shorter, and shorter. Okay. We are going to see something here that when we have, let's say we have the 5 to 5.1, and then it's get 49.49 meter per second. And then if we take 5 to 5.05, we have 49.245 meter per second. And then if we have, let's say 5.01, we get 49049. And then if we take smaller distance between these two positions, it means that the shorter should make the time shorter. Let's say this is 001. We have 490049. So we are getting something. It's getting closer, right? It's getting closer to this 49. It seems that, okay, that our average or our velocity getting close to 49, right? Okay. Now, what we have here is actually, if we take our equations into the graph, we could see that when we approach this, okay, we approach this, and then this A can be any time, and then we can make it shorter and shorter. And okay, it's similar to what we had before, right? We get in this secant line, and then if you imagine that there is tangent line here, it's getting close to that tangent line. So the secant line getting close to tangent line. Okay, now let's see on the bottom side here. What we call here, when we are getting close to this, the slope of tangent line, we can also say that is our definition of instantaneous velocity. Okay? So, if you remember here, we have really short time. So you could say after 5 seconds, like there will be like a quick, like really short after 5 seconds, we could calculate that velocity using limit. And that is what we call the instantaneous velocity. So with the same concept of limit, so we could say that instantaneous velocity, it means that instantly after that 5 seconds, okay? According to the question. Or if you want to define clearly, it is the velocity that appears instantly at that time. Okay? Or you could say it's the tangent at that point, the slope at that point when we compute a function. Okay. So when we have a function, if we know the tangent of that point, we can also have a similar definition with the instantaneous velocity. Okay? It's actually the same tangent line, the same slope. Okay? Right. So that is the first part of limit, the tangent problems and the velocity problems. Okay. Now the next part is going to be the definition of limit in terms of calculus. Okay. Okay, we start with the limit of a function. Okay. Okay, let's see this graph here. Okay. We have a function that is defined as x minus 1 over x squared minus 1. Okay? Now remember, as I mentioned in the previous sections in function, we need to keep this. Okay? Do not ever cancel this. Okay? And then we'll be making a new function. Okay? So if you see what we have, we are going to see some point that is using white dot here. It means that it's having some hole. There is a hole here, exactly at x equal 1. Because at x equal 1, it's not defined, right? Okay, we are going to have a break.